In this video, we're going to go and properly define convergence. Then we're going to review summation properties, and then we're going to finish off by learning our first series and our first test. So to understand convergence, we need to first talk about partial sums. So for example, let's say n equals 3 here. This would mean the sum of the first three terms of this sequence A. The first term plus second term plus the third term. And adding these up would give us a sum of three terms. More generally, we can say that for an n number of terms, we would get an nth partial sum, or the addition of n terms of this sequence. So now knowing this relationship, we can call this a function of n, and this function just returns the nth partial sum adhering to the sequence. So now what we're going to do is we're going to take the limit of f of n as n goes to infinity. What we're doing is we're seeing the behavior of the sum as we keep adding more and more terms. If this sum of infinite terms goes to a finite number, then if this is true, we can say that the sum from the first term to the infinite term of a of I is convergent. Now, if this sum does not go to a finite value, then that's divergent. So remember how in the improper integrals video, we just kind of glossed over convergence as if it's finite, it's convergent. If it's infinite, it is not. That's still true, but this is just a more mathematically rigorous approach to proving that. So now we're just going to quickly revisit properties of sums. And you've already seen this in the integration videos when we went over finite sums. But even though these are infinite sums now, the properties still apply. If we have a constant being multiplied to our sequence rule, then we can just pull the constant out and then say this is just the constant times this sum. If we have a sum or difference of sequences inside the series, then we can split into two series. And we know this is A and this is B. So this must be capital A plus minus capital B. Now we're going to talk about our first test for divergence called the nth term test. So imagine you have a series of infinite terms following some sequence A. Let's assume this is convergent. Remember back to the beginning of the video when we first talked about the definition of convergence. If this is convergent, then that means the limit as n goes to infinity of the nth partial sum is finite. So if this was true, then the graph of s sub n as we increased in n would look something like this, where it tapered off towards some value as we increased n to infinity. Notice that for this to happen, we're adding a smaller value to each sum every time we increase in n. That means the sequence here must do something like this. The sequence must eventually decrease to 0 to make these additions negligible for the sum to settle on a finite value. Mathematically, we can represent this as the limit as n goes to infinity of the sequence A is 0. This must be true for a convergent series. So if this must be true for a convergent series, then on the reverse, if this is not true, then the series must be divergent. If the limit as n goes to infinity of the sequence is not 0, then we 100% know that the series is divergent. But if it is equal to 0, then we know that it could be divergent. And as an example, consider this infinite series of 1 over n. Even though the limit as n goes to infinity of 1 over n is indeed 0, this in fact diverges. And this shows that while this is true, the reverse of it is not. The reason the nth term test can only test for divergence is because it doesn't tell us anything about the speed at which these sequences go to 0. I have here two series which sequences both go to 0, like so. However, this doesn't go to 0 as fast as this one. This is divergent, whereas this sequence goes to 0 fast enough such that it is convergent. This is really important for you to know so that you don't mess up on using the nth term test and test for convergence too. The nth term test, again, only tests for divergence. Now we're going to look at the first series that we're going to cover in AP Calculus called the geometric series. And the premise of the geometric series is that between every term, there's a common ratio r. And this is the only kind of series that you'll algebraically find the sum of in AP Calculus, and I'm going to show you how to do that. So we're going to begin by noting that both forms of these geometric series are the same thing. Doing a term-by-term expansion, you can see that this and this are equivalent. And now I'm just going to let S represent the infinite sum of the series. Now I have these two expressions of the same sum. And to the second one, I'm going to multiply by R, and you'll see why in a second. So by multiplying by R, I've raised the power of R by 1 in every term. And so now what I'm going to do is I'm going to take S and subtract RS from it. And so this difference expands to this, where these are both infinite sums. Notice that with this minus, this becomes minus AR, canceling this. This becomes minus AR squared, canceling this, and so on. And you'll see that every single term cancels except A and AR to the n. And this kind of series where the sums cancel themselves is called a telescoping series. So now continuing with the algebra, I'm going to factor out an S here on the left, and I'm going to factor out an A on the right. Now I'm going to solve for S, like so. And we can simplify this expression to this. So this expression represents the partial sum of n terms in the series. We want the sum of infinite terms to exist, so the limit as n goes to infinity of the sum has to be finite. So this means the limit as n goes to infinity of this must exist. But before we see how this limit can exist, I'm going to simplify it first. Using limit properties, we can break this into two limits, like so. Now notice that there's no n in this term here, so we can actually just get rid of the limit. So now we have to figure out when this limit exists. Since a over 1 minus r is a constant, we can just pull it out of the limit, like so. Now let's think about the behavior of an exponential function. What this really means is we're multiplying r by itself n times. And so if this increases, then as n goes to infinity, r to the n will also go to infinity, since with every multiplication of r, this total result gets bigger and bigger. We have to choose an r that makes the result go smaller. So the general rule is if r is bigger than 1, then r to the n will go to infinity, because every time you multiply by r, you're multiplying by something bigger than 1, which increases the value of this total result. Now, on the other side, if r is less than 1, then this goes to 0, because r less than 1 is a fraction, so you're taking a fraction of the last result, which makes it go smaller and smaller and smaller. So now we figured out that if r is greater than 1, this limit will go to infinity, and if r is less than 1, this limit goes to 0. Or, if r is greater than 1, the sum of the series is divergent. And if r is less than 1, then this is 0, so this cancels this out of the total sum expression, and we're just left with a over 1 minus r, which is finite, so this makes it convergent. And this proof leads to the result that the infinite sum of ar to the n is equal to a over 1 minus r, given that r is less than 1. And by the way, if r equals 1, then this series just turns into, which is just a times infinity, which is infinity, which is divergent. Now you know how to find the sum of a geometric series and when this formula can be used. For this example, we're going to use the nth term test to make some conclusions about these three series. So first I have the series of n cubed plus 2n minus 1 over n squared minus 5. All we do for the nth term test is just take the limit as n goes to infinity of our sequence. And now to evaluate the limit, I'm going to start by multiplying the top and the bottom by 1 over n squared. And this simplifies to this. And as n goes to infinity, this goes to 0, this goes to 0, this goes to 0, but this goes to infinity. So we just have infinity over 1, which is infinity. So since the limit of the sequence is not 0, we can conclude that this series is divergent. Now for the second series, 2 to the n plus 1 over 2 to the n plus 1, what I'm going to do again is I'm just going to take the limit as n goes to infinity. I'm going to start by separating this exponent. And then I'm going to pull out this 2 in the denominator to the outside of the limit. And then I'm going to split this fraction into two fractions. And now, if n goes to infinity, 2 to the n goes to infinity, which means 1 over 2 to the n goes to 0. And this 1 doesn't have any n's on it, so it's unaffected by the limit. So the limit of the sequence is equal to 1/2. And since this is not 0, this series is also divergent. The third example, we're going to use the nth term test on the series n over 6n squared minus 5. Again, I'm just going to take the limit as n goes to infinity and see what I get. And I'm going to begin by dividing the top and bottom by n, which simplifies to this. And so we see that as n goes to infinity, 5 over n goes to 0, and 6n just goes to infinity. So this goes to 1 over infinity, which goes to 0. The limit of this sequence is 0, but the nth term test only tests for divergence. So from this result, we can't make any direct conclusions about it, and we have to say that the nth term test is inconclusive for this series. That's how you use the nth term test. To close the video, we're going to find the sums of these three geometric series if the series are convergent. It's always good practice to begin by checking if it's convergent before actually going ahead and finding a sum. We have our a is 3 and our r is 1/2. So remember, when r is less than 1, the series is convergent. Since 1/2 is less than 1, we can use the geometric series sum formula to find our sum. So the formula is a over 1 minus r, and in this case a is 3 and our r is 1/2. So this is 3 over 1/2, which is 6. And that's the sum of the series. Same deal here, but we have to find the value of pi over e to check if the series is convergent or not. Pi over e is roughly 3.1415 over 2.7182. Since pi is greater than e, this will be greater than 1. And so since this ratio is greater than 1, the series is divergent, and so the sum is infinity. But for this third one, it's not immediately obvious what our ratio is or even our first term. We have to unpack the series a little bit before we can find that out. First, I'm going to split these exponents inside our series, like so, and note that 11 squared is 121. We can bring out 9 over 121 to the outside of this fraction, and that leaves us with this. But notice that 9 is to the nth power, and 11 is also to the nth power. So we can rewrite this as just one fraction, 9 over 11 to the nth power. And here we see the form that we're looking for, a r to the n. Since our r is less than 1, we know that this series is convergent and we can find the sum. So remember, the sum is a over 1 minus r, and here a is 9 over 121, and our r is 9 over 11. And this simplifies to this, which simplifies to this, which is equal to 9 over 22. And that's the sum of the series.